Today we're diving into the CAP Theorem, a foundational concept in distributed system design. Introduced by Eric Brewer in 2000, the CAP Theorem helps us understand the unavoidable trade-offs when building systems that span multiple computers or locations. Whether you're a developer, architect, or just curious about how large-scale applications work, understanding CAP is essential. We'll break down what CAP stands for, why it matters, and how it shapes the systems we rely on every day. Let's start by exploring the three pillars of CAP: consistency, availability, and partition tolerance. EAP stands for consistency, availability, and partition tolerance. These three properties define the core challenges in distributed systems. The theorem states that it is impossible for a distributed data store to simultaneously provide all three guarantees. This means, when designing a system, you must make tough choices about which properties to prioritize. Each property addresses a different aspect of system reliability and user experience. In the next scenes, we'll break down each pillar and see how they impact real-world systems. Consistency means that every read receives the most recent write or an error. In other words, all nodes in the system return the same data at any given time. This is crucial for applications where up-to-date information is vital, such as financial systems. Imagine transferring money between accounts. You want every balance inquiry to reflect the latest transaction. Consistency ensures data accuracy, but achieving it can come at the cost of other properties, especially during network issues. Availability guarantees that every request receives a response, even if it doesn't contain the most recent data. This means the system remains operational and responsive no matter what. For example, online retail systems like Amazon prioritize availability, so customers can always add items to their cart, even during high traffic. While this keeps the system running, it may sometimes return outdated information. The trade-off is between always being up and always being correct. Partition tolerance means the system continues to function even if network failures split it into isolated groups. In distributed systems, network issues are inevitable. Partition tolerance ensures that the system can still operate, even when some nodes can't communicate. For example, during a network outage, some parts of the system may be cut off, but the rest keeps working. This property is essential for any system that spans multiple locations or relies on the internet. Heart of the CAP theorem is its impossibility result. No distributed system can guarantee consistency, availability, and partition tolerance all at once. When a network partition occurs, you must choose between being consistent or being available. This trade-off is at the core of system design decisions. Understanding this limitation helps architects make informed choices based on their application's needs. When a network partition happens, you can either choose to be consistent or available, but not both. If you choose consistency, some requests may be rejected to ensure all nodes have the same data. If you choose availability, the system will respond to every request, but some responses may not reflect the latest data. This dilemma is the essence of the CAP trade-off and shapes how different systems behave during failures. CAP systems prioritize consistency and partition tolerance, but may sacrifice availability during network partitions. Traditional relational databases like MySQL and PostgreSQL, when configured for strong consistency, are examples. In banking, for instance, it's more important to have accurate data than to always be available. During a network issue, these systems may reject requests to prevent data errors, ensuring that all nodes remain in sync. CAP systems focus on availability and partition tolerance, potentially sacrificing consistency. NoSQL databases like Cassandra and DynamoDB are designed this way. For example, Amazon's shopping cart system always lets you add items, even during network issues. This approach ensures the system is always responsive, but sometimes at the cost of returning outdated or inconsistent data. It's ideal for applications where uptime is more important than perfect accuracy. EA systems offer both consistency and availability, but only when there are no network partitions. In practice, this is only possible in single-node databases or systems that don't span multiple locations. In distributed systems, network partitions are inevitable, making this combination impractical. However, understanding CA helps clarify why distributed systems must make tough trade-offs. Let's look at a real-world example: banking systems. When you withdraw money from an ATM, the system must ensure your balance is updated everywhere to prevent overdrafts. Here, consistency is prioritized over availability. If there's a network issue, the system may block transactions rather than risk inconsistent balances. This approach protects both the bank and the customer from errors. E-commerce availability is often more important than strict consistency. For example, Amazon's shopping cart system is designed to always accept items, even during high traffic or network problems. This ensures a smooth user experience, though it may occasionally show outdated cart contents. The system later reconciles any inconsistencies, prioritizing uptime and customer satisfaction. Eventual consistency is a practical strategy for many distributed systems. It means that over time, all nodes will converge to the same data, but not immediately. This approach is suitable for applications where immediate consistency isn't critical, like DNS or content delivery networks. Eventual consistency provides a good balance between availability and performance, making it popular in large-scale systems. Strong consistency ensures that once a write is confirmed, any subsequent read will return that value. This is essential for systems where data accuracy is non-negotiable, such as financial applications or inventory management. While strong consistency provides reliability, it can impact system availability, especially during network issues. Choosing strong consistency means prioritizing correctness over uptime. Stable consistency allows systems to adjust their consistency levels based on specific needs. For example, Cassandra lets you configure how many nodes must agree before a read or write is considered successful. This flexibility enables applications to choose stronger consistency for critical operations and weaker consistency for less important ones. Tunable consistency is ideal for platforms with diverse requirements, like e-commerce sites. Quorum-based approaches use voting among nodes to ensure a certain level of consistency and fault tolerance. In these systems, a majority of nodes must agree on an operation before it's accepted. This balances consistency and availability, and is often used in consensus algorithms like Paxos and Raft. Quorum systems are common in distributed databases and are key to building resilient architectures. CAP is foundational, it doesn't cover every scenario. The PACLC theorem proposed by Daniel Abadi extends CAP by considering latency and consistency even when there's no partition. PACLC states, if there's a partition P, the trade-off is between availability A and consistency C, else E, the trade-off is between latency L and consistency C. This model acknowledges that even in normal operation you must balance speed and accuracy. Choosing the right balance among consistency, availability, and partition tolerance depends on your application's requirements. For financial systems, prioritize consistency. For social media or e-commerce, availability may be more important. Understanding CAP helps you make informed decisions, ensuring your system delivers the right user experience and reliability. Always consider your users and business goals when making these choices. Sum up, the CAP theorem teaches us that distributed systems can't have it all. You must choose 2 out of 3: consistency, availability, and partition tolerance. Each choice comes with its own set of trade-offs and impacts how your system behaves during failures. By understanding these principles, you can build more robust, scalable, and user-friendly applications. In designing distributed systems, always start by identifying your application's priorities. Do you need absolute accuracy, or is uptime more important? Use strategies like eventual consistency, strong consistency, or tunable consistency to match your needs. Remember, there's no one-size-fits-all solution. The best system is the one that aligns with your goals and user expectations. Thanks for joining this exploration of the CAP theorem. By understanding the trade-off between consistency, availability, and partition tolerance, you're better equipped to design resilient distributed systems. Continue learning about related concepts like PACLC, consensus algorithms, and real-world architectures. Stay curious and keep building systems that make a difference.